Today I'm going to present a video on Introduction on Limit State Method of Design. Please subscribe to Civil eLearn for more videos. Limit State Method. In this method of design, a structure is designed to withstand safety when all the possible loads, that is dead loads, live loads, wind loads, earthquake loads and snow loads that are likely to act on it throughout its lifetime. In addition to the design, in the limit state method, we will check the structure for serviceability requirements such as limitations for deflection and cracking. Different types of limit states. These are all the different types of limit state of collapse and limit state of serviceability. Limit state of collapse. In this, we are having four types. That is for flexure, that is for beams, for compression, for columns, for shear, and torsion. After designing the structure for limit state of collapse, we will check the structure for limit state of serviceability, that is deflection, cracking, and other limit states such as vibration, fire resistance, and durability. Limit state of collapse. In the limit state of design, the structure is normally designed for limit state of collapse and checked for limit state of serviceability. As I already told, the collapse of structure occurs by failure of its member either in flexure, shear, torsion, bond, axial compression or tension, or by combination of all these. The strength of the member at limit state of collapse is known as the ultimate strength of that particular structure. These are the assumptions made in the theory of bending of RCC members for flexure. A normal section before bending remains plane after bending right up to collapse. The ultimate state of collapse is said to have reached its flexure when maximum compressive strain in concrete in the outermost fiber reaches its ultimate crushing strain. The IS code prefers the maximum compressive strain in concrete is equal to 0.0035, even though it varies with grade of concrete between 0.002 to 3 to 0.005. So we will assume that the maximum compressive strain of concrete is 0.0035. Concrete under tension is ignored. In this case, we are assuming that the total tension is taken by the steel and the total compression is taken by the concrete itself. The distribution of compressive stress in a concrete across the section is defined by an ideal stress strain curve of concrete. I will show in next slide. What about the stress strain curve of concrete? Perfect bond exists between concrete and steel up to collapse. There should be a perfect bond between the steel and concrete. Surrounding concrete should be perfect. As per IS code, the maximum strain in steel in tension shall not be less than 0.002 plus Fy divided by 1.15 ES. In this case, Fy means yield stress and ES means modulus of elasticity of steel. Ultimate moment of resistance. This is the maximum resisting moment offered by the section due to its internal stresses against applied bending moment at collapse, that is factored bending moment, is called ultimate moment of resistance. In this case, we are having two moments of resistance, that is bending moment and factored bending moment. Factored bending moment means which can be multiplied with the factor of safety. We will get the factored bending moment, that is 1.5 into bending moment, we will get the factored bending moment. Types of beams. Generally, we are having three types of beams. In this case, singly reinforced beam, doubly reinforced beam, flanged beams. Singly reinforced beam means the reinforcement in the beam is provided only in the tension zone. That particular beam is called singly reinforced beam. Doubly reinforced beam means the steel in the beam shall be provided both in compression zone and in tension zone. Flanged beam means we are having two types of flanged beams, that is T beams and L beams. Singly reinforced beam, the beam having reinforcement only on tension side, which is known as singly reinforced beam. So this is the cross section of that particular beam, which is having a B width and capital D small. Capital D is the total depth of the beam, and from center to top of the beam, that is small d, that is effective depth. And this is the tension reinforcement, that is AST, and this is the strain value. In this case, the strain in the steel is 0.002. In this case, it is x1 and this is x2. Totally, the neutral axis falls at a section of x, and the maximum strain in concrete is 0.0035, and here the maximum strain in steel is 0.87 Fy by Es plus 0.002. This is the stress diagram of this particular rectangular cross section. Here we will get 0.446 FCK, and this is the total compression point which will act at a point from the top of the beam, and the distance between the total compression to total tension, that is Z, which is also known as Leverarm. We already studied in the previous video, and the total tension is 0.87 Fy. So total compression Cu is equal to 0.36 FCK Px nu. This is the stress strain curve for concrete. This is the parabolic curve for FCK, that is characteristic compressive strength of concrete. This is 0.67 FCK. This is 0.67 FCK by gamma m, that is partial safety factor. Here, if we multiply divided by 1.5, we will get 0.446 FCK. So this is the strain in concrete, that is 0.002, and this is the maximum strain in concrete, that is 0.0035. This is the stress block parameter. In this case, the total compression is located at a distance of 0.42 x nu, and the total compressive stress is equal to 0.36 FCK Bx nu, and this is the x nu, that is neutral axis depth. So the relation between the compressive stress distribution in concrete and the strain in the concrete may be assumed as rectangle, trapezoid, and parabola. So the area of stress block is equal to 0.36 FCK Bx nu, and the depth of center to compressive force is equal to 0.42 x nu, which is already given in the IS 456 2000. And this is the stress strain curve of a steel bar. So in this case, we can see this is the Fy graph, and this is Fy divided by 1.15, that is Fy divided by gamma m. Gamma m is equal to 1.15 for steel, and Es is equal to 2 into 10 power 5 Newton per mm square. And this is the stress strain curve for defining yield point, same Fy divided by 1.15. So the maximum compressive stress in concrete in the outermost compression fiber, by considering the partial safety factor, that is 0.67 FCK divided by 1.5, which is the factor of safety of concrete, we will get 0.446 FCK. Then depth of parabolic portion of the stress block can be obtained from the stress strain diagram. So if we want to find out the depth of the parabolic portion, that is x value, we have to analyze this particular section. So from similar triangles property, x1 divided by 0.002 is equal to x divided by 0.0035. So let us take the similar triangles in this particular section. X divided by this particular value and x2 divided by this particular value, we will get x1 is equal to 4 by 7 into x. Similarly, the depth of rectangular portion of the stress block, x2 divided by 0.0035 minus 0.002 is equal to x divided by 0.005. Here we will find out x2 is equal to 3 by 7 x. So these are all the values of x1 and x2. by using similar triangles property, then C1 is equal to area of the parabolic stress block into width. So C1 is equal to 2 by 3 into 4 by 7 x into 0.446 into B, that is width. Force of compression in the rectangular stress block, that is C2 is equal to area of rectangular portion into width. C2 is equal to 3 by 7 into x into 0.446 B. Then total compressive force C is equal to C1 plus C2. By adding C1 and C2, we will get C is equal to 0.36 FCK Px nu. Just calculate the area of this particular trapezoidal portion and this rectangular portion and this parabolic portion. We will get the total C value, that is C is equal to 0.36 FCK Bx nu. Then let us calculate the A value. A value formula is C1 into x2 plus 3x1 by 8 plus C2 into x2 by 2 by total compression. We will, by substituting the C1, C2 and C values, we will get A is equal to 0.416 x nu. That is A is equal to 0.42 x nu, which is from the top of the beam to that particular force. The depth of neutral axis is obtained by considering the equilibrium of forces, that is total compression is equal to total tension. In this case, the resultant force of compression is 0.36 FCK Px nu. The resultant force of tension is equal to 0.87 Fy AST. So by substituting, by equating this particular equation, we will get x nu by d is equal to 0.87 Fy AST divided by 0.36 FCK BD. By using this formula, we can calculate the depth of the neutral axis, the Leverarm. As we already seen in the previous video, the distance between the line of action of two forces is called Leverarm, that is from tension to compression, that is Z is equal to d minus 0.42 x nu. Moment of resistance with respect to concrete is equal to total force into Leverarm, that is 0.36 FCK B into x nu into Z. With respect to steel also 0.87 Fy into AST into Z. So here we are having x nu max by d values, which is given in the IS 456 for different types of grades of steel. That is for Fe 250 it is 0.53 and for 415 it is 0.48, and for Fe 500 steel xu max by d is equal to 0.46. In this case also we are having three types of modes of failures, that is balanced section, under reinforced and over reinforced. If x nu by d is equal to xu max by d, the section is balanced, and if it is less than, the section is under reinforced, and if it is greater than, the section is over reinforced. The limiting values of tension steel and moment of resistance, that is mu limiting with respect to concrete, is equal to 0.36 FCK B x nu into Z. In place of x nu, we will substitute xu max for limiting section, that is 0.36 FCK B xu max into d minus 0.42 xu max. As we already seen in the previous slide, the xu max by d values for different grades of steel. By substituting the xu max by d value in this particular equation, we will get the generalized equations of 0.148 FCK BD square for Fe 250, 0.138 FCK BD square for Fe 415, and 0.133 FCK BD square for 500. If we substitute the FCK values of 50, 20, 25, different grades of concretes, we will get the equations, mu limiting equations for different grades of concretes. The percentage of tensile steel corresponding to the limiting moment of resistance is obtained by the equation of force of tension to force of compression. By equating these two values, we will get the AST value. Then PT limit is equal to AST by BD. This is the maximum and minimum tension reinforcement formulas as per IS 456. That is AST by BD is equal to 0.85 by Fy. By substituting all the values, we will get the minimum AST value, and the maximum reinforcement formula is 4% of gross cross-sectional area, that is 0.04 into B into capital D. Thank you for watching.